we should get started because I don't want to keep people too late. So I'm very happy that our final speaker for the day is Kęstutis Česnavičius from Paris-Saclay. And he's going to tell us about the Perfectoid approach to purity questions.
Thanks a lot. And thanks to the organizers for the invitation to speak at this symposium in honor of Peter Scholz's Fields Medal. It's a great honor to be able to give a talk here, and it's also a pleasure to speak about questions really in commutative algebra or algebraic geometry, classical questions, much like those discussed in Ivan Dre's talk. Questions to which answers involved Perfectoid techniques in heavy way, although a priori these questions do not have so much in common with Perfectoids on the face of it, or even with periodic geometry. So I will talk about purity questions, and the purity, and specifically about the Perfectoid approach to attacking such questions. I will discuss several instances in which this approach was successful. But to begin with, let me just tell you right away what I mean by purity, because it's actually something else than what appeared in Ivan Dre's talk. For me, and in this talk, purity is somehow a phenomenon of insensitivity of certain invariants of say schemes or rings, invariants, insensitivity of invariants to removing subschemes which are small in perhaps small subspaces, which are small in some sense. So let me begin with a very basic example of this, just to illustrate what this abstract principle means. It's perhaps the most elementary setting in which purity is witnessed. Is the Hartog's extensional principle from several complex variables. Really, precise statement is that if we have an open subset U of complex space Cn, where n is at least 2, so that's okay. That's critical actually. Okay, so and we have a compact subset K of U such that the complement of this K is connected, which is the meaning of small in this particular instance of purity. Then the statement is that the homomorphic functions are unaffected by removing this K. So homomorphic functions on U are the same as homomorphic functions on the complement U minus K. The map, of course, being given by simply restricting function to this complement. Okay, that's an example from complex variables. Really, it's far from arithmetic geometry or algebraic geometry that we'll discuss in this talk. So let me switch really to discussing the goal of what purity we seek. So the goal is really the analogues of such phenomena, of such insensitivity, analogues for invariants that appear in arithmetic geometry. So for arithmetic invariants, For example, for the étale fundamental group, for étale cohomology, with say torsion coefficients or simply constant coefficients for simplicity, I don't know, for the Brauer group, for example, or some sets of torsors, for more complicated cohomology theories such as flat cohomology, and there are many other invariants that we consider, algebraic K-theory, that motivic cohomologies that appeared in previous talk, being some for which such phenomena could also be considered. So let me just right away mention the results, the purity results for these invariants that are known. So for the étale fundamental group, this is the Zariski-Nagata purity, which in the generality of arbitrary regular schemes was proved by Grothendieck in SGA2. For étale cohomology, again, X being regular, purity was proved by Gabbard-Thomasson and conjectured by Grothendieck. This was the absolute cohomological purity conjecture of Grothendieck. For a Brauer group, this was proved in most cases by Gabbard, using various methods, and in some remaining cases which were particularly stubborn, this was completed using perfectoid techniques. In fact, this cases where the perfectoid approach to such questions originated, and we developed it further in joint work with Scholze, which addressed the case of flat cohomology, again of regular or more generally complete intersection schemes X. So let me switch to actually giving precise statements. So for instance, I will discuss all of these, or really all of these in what follows. And let me begin by giving a precise statement with precise hypotheses of what purity is, for instance, for étale cohomology, the Gabbard-Thomasson purity. This will also be the basic example in which a perfectoid strategy is already fruitful in giving a new argument for this result. So the assumptions are that we have a Noetherian regular scheme X. That's our space, and we have a closed subspace Z in X, which we would like to remove and witness the insensitivity of étale cohomology to doing so. And the coefficients will be given by Z mod NZ for simplicity's sake, where N is invertible on X. Then, the étale cohomology of X with coefficients in Z mod N, these cohomology classes restrict to the complement of Z and give étale cohomology classes there. And this restriction map is, according to this theorem of Gabbard-Thomasson, is injective if I is less than twice the codimension of Z in X, and is bijective in degree 1 lower if I is less than twice the codimension of Z in X minus 1. So that's purity for étale cohomology. Equivalently, one notice right away that this insensitivity to removing Z is in fact expressed as vanishing of cohomology with supports in degrees less than twice the codimension of Z in X, cohomology of X with coefficients in Z mod NZ. This cohomology with supports being the term that fits in the long exact cohomology sequence of cohomology with supports, and which controls the kernel of this kernel and co-kernel of this kind of map. All right, and so in terms of this reformulation of cohomology with supports, one reduces the purity question, this insensitivity, to removing Z. There is somehow a local global principle which comes from the fact that cohomology with supports is a cohomology of sheafified cohomology with supports, and so one reduces to the local case when X is just spec of R for a regular local ring R, and well, by a further devisage, the essential case is when Z is simply the maximal ideal in R. And one is studying the étale cohomology of a regular local ring and of its puncture spectrum. One is wondering whether the two are the same. And in this setting, the Gabor-Thomas purity for étale cohomology is the statement that the étale cohomology with supports in the maximal ideal and coefficients in Z mod n vanishes for in cohomological degrees less than twice the dimension of the ring. Well, so far this has on the face of it is just a question about étale cohomology. There's nothing to do with p-adic geometry or so, in which perfectoid, well, which is really the domain of where perfectoids have occurred, although later it also branched into commutative algebra, and this is somehow how the link appears. The point is that the most delicate case of such statements is when R is of mixed characteristic 0p, basically because in equal characteristic irregular local ring, its completion is just a power series ring over the residue field by Cohen structure theorem, and in mixed characteristic, of course, also is a Cohen structure theorem, but the structure is, especially in the ramified case, a lot more delicate. And it's these cases in which these cohomological problems tend to be the most difficult, as we already well briefly heard about in the previous talk. For instance, the Gersten conjecture for algebraic K theory is known in equal characteristic, but in mixed characteristic it remains open. Gersten conjecture, by the way, also being a purity phenomenon. So it is in this case where the perfectoid approach to such questions has been particularly helpful. In fact, it's what allowed making progress on these questions in situations where other methods failed. And let me illustrate this method. Let me summarize this method in the case of this étale cohomology. Simply for concreteness, later I will switch to discussing other cases as well. And in fact, this case of étale cohomology is this. The strategy is particularly close to the initial application of perfectoid spaces, namely to the proof of the weight monodromy conjecture for complete intersections in smooth projective toric varieties. In fact, the strategy is very much similar, and the first step is to replace R by a perfectoid cover, build a highly ramified extension R infinity of R, such that this ring R infinity is perfectoid, or integral perfectoid, as is sometimes called, although okay, and reduce the problem the problem at hand to its counterpart, or to some to the appropriate problem in the perfectoid setting for this R infinity. For example, in the case of étale cohomology, what we end up needing to show if we proceed in this way is the corresponding vanishing of étale cohomology with supports still at the maximal ideal for I in cohomological degrees, again less than twice the dimension of the ring of the regular ring R, of which R infinity is a perfectoid cover. And R infinity, well, we already saw that actually in Yves André's talk. For example, if R is the power series ring in mixed characteristic, somehow a very basic mixed characteristic case, then R infinity is obtained from R by adjoining all p power roots of P and all the p power roots of these standard coordinates, and then p-adically completing the result. Okay, so that's somehow the first stage of the overall approach, and the second. So in a setting of weight monodromy conjecture, there's somehow this kind of step corresponds to passing from your variety over say finite extension to QP to a variety to its base change over some perfectoid field, a large extension of QP, which nevertheless sees enough information about cohomology so that the relevant cohomological information is not lost. The second step is what in that case, in the case of weight monodromy, corresponds to tilting. Here, in the case of étale cohomology, one again, so the strategy is to reduce the positive characteristic via tilting, or I mean, for some problems that suffices. For étale cohomology, it is the case, or argue directly, or argue using somehow tools from perfectoid geometry, tools that have been developed later. So well, for passing to the positive characteristic, that's of course tilting. The techniques from perfectoid geometry I have in mind are some prismatic techniques, or using arc descent of Bat Matthew to reduce to simpler perfectoid rings, using techniques from derived algebraic geometry to add flexibility to the intermediate reductions, are some of the tools that appear on the stage. And so let me switch to being more concrete, and by surveying the purity results that were settled following this approach. So technically, perhaps the simplest is a new proof of Gabbard-Thomason purity. Gabbard-Thomason purity for étale cohomology. This is in our joint work with Scholze. And it is somehow technically least, I mean, most straightforward, because tilting simply works, and when reduced to an analogous problem in mixed characteristic, equal characteristic, where it is easier to handle because the completion of regular local ring in equal characteristic is just a power series ring. But in fact, it has this application arose somehow by inspecting the other results proved this way, of which, well, the first application of these purity techniques, of these perfectoid techniques to settling purity questions was for purity for the Brauer group. So this was a conjecture of Grothendieck and Auslander-Goldman, which Gaber has settled in many cases. In prior works, there were some cases left in mixed characteristic where his techniques did not seem to suffice, and it was in Bonn with discussions with Peter where this result came out, and it turned out that the perfectoid approach yielded these remaining cases. So the precise statement here is that if we have a regular local ring R with maximal ideal M, and the smallness assumption, the smallness of the complement of maximal ideal is now the assumption that the dimension of R is at least 2, then the Brauer group of R, defined in terms of Azumaya algebras and the Brauer equivalence of Azumaya algebras, is insensitive to removing this maximal ideal. The Brauer group of R is the same as the Brauer group of the punctured spectrum of R. And more concretely, the Brauer group of R is the intersection over all primes of height 1 in R of the Brauer groups of the localizations of R at this height 1 prime P, and this intersection is inside the Brauer group of the fraction field of R. This then leads one to the so-called residue sequence for the Brauer group, which is, for example, used in studying rational points in the Brauer-Mann abstraction in describing the Brauer group of varieties, analyzing rational equivalence and its relation to Brauer groups, so on. All right, and the third setting of where perfectoid methods were crucial for settling purity was in joint work with Peter. This was purity for flat cohomology. And this included two conjectures of Gaber, who raised them actually while investigating the purity for a Brauer group. He came up with certain more general statements which seem plausible, and these more general statements turn out to be special cases of this purity for flat cohomology, which in precise terms states that if we have a Noetherian local ring, well, of course, there are global versions of these statements, but let me just focus on the crucial local statements. So if we have a Noetherian local ring R with maximal ideal M, and where R is, say, regular, or more generally, a complete intersection, in the usual sense, is completion is a quotient of a regular ring by a regular sequence, and a commutative. So that's our base, and the coefficients for flat cohomology will be simply a commutative finite flat group scheme, finite flat R group scheme G, then the flat cohomology of R with coefficients in G. For example, G could be mu P. That's a case very much relevant for Brauer group. This vanishes for I less than a dimension of the ring, and even less or equal dimension of the ring if R is regular. If R is regular and not a field of dimension, of positive dimension. Okay, so let me switch to discussing some of the techniques that go into arguing these purity results, and I'll split them into two batches. First of all, techniques for passing to perfectoids, and then what we do at the perfectoid level to conclude. And in fact, it's in most of these problems, it's the first step that is simpler. So passing to perfectoids is simpler than actually settling the corresponding statements on the perfectoid level. So let me begin by discussing those. So, well, what are some of these techniques? So first of all, one wishes to replace the ring R with its completion, basically because one understands the structure of complete regular local rings much better. So one uses excision to pass to the completion. For example, one has excision for flat cohomology. This is actually something that we argued with Scholze, and the proof is somehow indirect, somewhat circuitous, and it uses perfectoids and also animated rings. There are the algebraic geometry and perfectoids to somehow, these techniques are used to somehow reduce this kind of statement about flat cohomology to the case when these R and R hat somehow perfect FP algebras. And anyway, I will discuss this in a moment. Let me actually mention in passing that such excision, we also have it for non-commutative, in a non-commutative setting, when G is not necessarily commutative, some group H. And let me write informally that these non-commutative H2 with supports are insensitive to completion. There's of course precise statements in terms of torsors or sections. Let me just abbreviate in this way. So here H is smooth, quasi-affine, and these are contained in joint work with Boutier. Okay, so that's for passing to the completion. It's in case of flat cohomology, this excision. In case of the Brauer group, it's some version, simpler version of these insensitivities for torsors, for PGLN torsors in that case, them being related to the Brauer group through Osmai algebras. And once one has a complete regular local ring of mixed characteristic 0p, one can build this R infinity pretty explicitly by extracting p power roots of regular system of parameters, one then uses spectral sequence and limit arguments to pass to the top of that resulting tower to climb up a perfectoid tower. And in the local complete intersection case, which, well, beyond regular rings somehow, one also uses André's lemma, which he also hinted at during his presentation earlier today. Roughly, if we have a perfectoid ring, such as a perfectoid cover of a regular ring, modulo some ideal, and we periodically complete, this quotient is only perfectoid if for each element of this ideal, it also has p power root, which belongs to that same ideal in the sense that the ideal is closed under taking p power roots of its elements. So in general, if we just extract these p power roots of coordinates, it does not mean that elements like x1 plus x2 automatically acquire p power roots, of course, if the x1 and x2 do, but André's lemma allows one to refine the cover further so that even such such elements do actually acquire these roots. And anyway, this is somewhat important technical input to passing to perfectoids in the case of complete intersections. Okay, so now what about the techniques at the perfectoid level? This is actually somehow the main step in all of these arguments, because somehow it's not, it's not so straightforward to settle these perfectoid analogs. But let me begin with the case of a cohomology, Gabbard-Thomason purity, where the required technique is simpler. So one uses the following result, which is tilting. Well, but an algebraic version of tilting, which in fact is simpler than the analytic version, or and its precise statement is as follows. So if we have this perfectoid ring A, or well, integral perfectoid, just to stress that we're in the setting of perfectoid rings as introduced by Bott-Morrow-Scholz, and not the perfectoid Tate rings as in rigid perfectoid rigid geometry. So we have a perfectoid ring A, and we give ourselves opens U of spec of A, and this open is supposed to contain the locus where P is invertible. The prime P is invertible. So such an open corresponds to an open of the tilt of the perfectoid, to an open U flat of the spec of the tilt of A, and so the correspondence is characterized by requiring that these opens have matching complements under the identification of A mod P with A flat mod P flat, where P flat is it's a compatible system of P power roots of a unit multiple of P as usual, and A mod P is then the same, is really isomorphic as a ring to A flat mod P flat, and so mod P and mod P flat loci of these perfectoids agree, and then the opens are supposed to match in that their complements as sets are just the same under this identification. Okay, so in this setting, the étale cohomology of U with, say, constant coefficient z mod n is the same as the étale cohomology of this open and positive characteristic U flat. That's tilting. That's this algebraic tilting. And well, why do I call it algebraic? So first of all, it's a statement that really is somehow in commutative algebra and rigid geometry, but maybe more importantly, the proof is also purely algebraic. It does not pass to perfectoid spaces. The proof of the theorem is based on P-complete arc descent. Of Bat and Matthew, who showed that étale cohomology satisfies arc descent, and well, there's also versions somehow for P-complete rings, P-complete arc descent for étale cohomology with P-completion and inverting P. And so one uses this kind of descent result, very much similar to what we saw in Matthew Morrow's talk just before. There was a CDH descent there, again reducing to valuation rings somehow. So okay, so we use this technique to reduce to A being a product of valuation rings of rank at most 1 and periodically complete valuation rings of rank at most 1 with algebraically closed fraction fields. So absolutely integrally closed periodic complete valuation rings, perfectoid valuation rings, and A being an infinite product of such, any perfectoid A admits a hypercover by perfectoid rings of this form, and one somehow can reduce this statement to such a case. The point of this reduction being that for such A, open subsets, quasi-compact opens of such A have no non-split étale covers. So effectively, only H0 étale is non-zero, is potentially non-zero, and somehow can argue and can match with positive characteristic directly. Because H0 étale is then defined by described by idempotence, at least with constant coefficients, and idempotence of A and of its tilt match because the tilt is as a multiplicative monoid is p-power compatible elements of p-power compatible sequences of elements of the original perfectoid A. So in fact there's a version of this also with coefficients. If one uses a slightly more sophisticated descent, not only for étale cohomology, but also for somehow étale fundamental group, this P-complete, well, this kind of arc descent was established by Matthew in subsequent work. So one can also obtain the version with non-constant coefficients. And namely for a commutative finite étale U group scheme G, there is a commutative finite étale group scheme G flat over U flat, and an isomorphism of a talc homology of U with coefficients in G, and the corresponding talc homology of U flat is G flat, now also being constructed via arc descent somehow. And so for purity for a Brauer group, to obtain purity for a Brauer group, one uses one applies this version with U being the locus where P is invertible, and G being mu P, and analyzing somehow in the case of a Brauer group, one has this somehow convenient fact that if one has an arbitrary U, then localizing it further, for instance, inverting P, cannot kill any Brauer classes, at least in the case in the regular context. That is a theorem of Grothendieck. And so one has this additional trick of being able to invert P and to pass to small open U, and obtain the and then in positive characteristic, one uses that the P cohomological dimension of any ring in positive characteristics, such as for example this one, is at most one, as follows from basically Artin-Schreier sequences, as was established by Artin in SJ4. Okay, the most delicate of these is the purity for flat cohomology, and in this case, the key perfectoid result is the following formula for flat cohomology in case of perfectoid rings. So the precise statement is that if we have a perfectoid A and a commutative finite flat group, commutative finite locally free A group scheme G of P power order, any G can be decomposed into its primary components, and it's the P primary ones that matter in this context, because the ones of order invertible on A, for them one can use a talc homology, and that's purity for a talc homology really. So of P power order, and a closed subset Z, again contained in a P equals 0 locus of A, contained in spec of A mod P, the flat cohomology of A with supports in Z and coefficients in G is given by a formula which relates it in terms of quasi-coherent cohomology of the ring A inf of A, and with coefficients in the prismatic Dieudonné module of this group G, Verschiebung invariance on this quasi-coherent cohomology. Let me call this formula star, because I'll discuss it in what follows. So here, of course, A inf of A is as usual just Witt vectors of the tilt of the inverse limit perfection of A mod P, and M of G equipped with its Frobenius automorphism, or really also with a Verschiebung endomorphism, and also with a Frobenius, is finitely generated A inf of A module of projective dimension at most one associated, that's associated to our finite locally free commutative group G via prismatic Dieudonné theory of Scholze. Prismatic Dieudonné theory by, so Scholze explained this in his Berkeley lectures, and this was later generalized by Anschutz and Lebras to a case of more general, for instance, quasi-regular semi-perfectoid rings in terms of really in a prismatic setting. Let me perhaps give a precise statement of what this prismatic Dieudonné classification says. So there is an equivalence. There's an equivalence of categories between group schemes finite locally free commutative G over a perfectoid A of p power order as in the theorem, and let's say anti-equivalence with finitely presented modules over the ring A and of A, modules of projective dimension at most one that are equipped with maps Frobenius. Okay, let's say modules M, Frobenius and Verschiebung maps, such that Frobenius is Frob semilinear, where Frob is a Frobenius of A. Verschiebung is Frobenius inverse semilinear. And the composition is multiplication by Frobenius twist by a kernel of generator of Fontaine's map theta, and composition in the other direction is simple multiplication by that generator psi. This being given by G goes to M of G, where M of G in prismatic terms is just the x1, prismatic x1 of G against the prismatic structure sheaf of the perfectoid of the perfectoid in question. Okay, so in the case of purity for flat cohomology, this is the key statement that one needs to show. This theorem, or really this equality, this identification of flat cohomology with quasi-coherent cohomology, and this in fact is rather indirect. So let me mention how one goes about proving this identification star. So first, one shows that both, well, overall, the strategy is as follows. One shows that both sides of this equality star satisfy pre-complete hyperdescent, so satisfy hyperdescent in the pre-complete arc topology on perfectoids A. And so, well, okay, in fact, most of the work perhaps happens here, and I will elaborate on that in a moment. But granted this, one uses this to again reduce to, as in the case of Étale cohomology, which by the way, actually came about by analyzing this argument and also realizing that it could be adapted to the case, to a much simpler case of a cohomology. Anyway, one reduces this to the case when A is p-complete product of p-complete evaluation rings of rank at most one with algebraically closed fraction fields. Again, in this case, even though the ring is somewhat horrible, just ring theoretically, it has good cohomological properties. In the case of a cohomology, I've mentioned that any quasi-compact open of spec of this product has no non-split non-split at all covers. And similarly, one can analyze flat cohomology. It's only concentrated degree 0, and 1. And so somehow one can check by somewhat explicit analysis that this star, this identity star for such A holds, well, more or less directly by hand explicitly. Okay, so well, in a view of the strategy, really the main work, granted that our identification in the case of when A is this big infinite product, this identification is of course functorial and natural and so on. The main point is to show that both sides satisfy hyperdescent for p-complete arc topology. This is significantly simpler for the right-hand side, or at least it required. I mean, it was direct to reduce from the literature. It was essentially done already. For the right-hand side of star, the quasi-coherent side, somehow the p-complete arc descent follows from results of Batt and Scholze, follows from the fact that the functor which assigns the perfectoid A, either, for example, A itself or its tilt, or the A inf of A, this functor is a p-complete. Okay, these functors, they are p-complete arc sheaves on perfectoid inputs A. So this is a result of Batt and Scholze in their prismatic paper. Really, essentially, it's contained. The essential input is, in fact, in their paper on with vector alpha and Grassmannian. The key point is that the functor which the perfect FP algebra associates its vector bundles satisfies V descent, and somehow it's all bootstrapped from that. This and then the descent for the right hand side of this identity. So the key point is the left side, and this in fact is somewhat indirect. So for flat cohomology, for the left hand side of this identity star, arguing p-complete arc descent is somehow indirect, and in turn it proceeds as follows. So first one proves the star, this identity in positive characteristic. In positive characteristic, namely for perfect FP algebras, for perfect FP algebras A. One advantage of that is that then one can drop the z because, I mean, there's no restriction on z anymore. And so one can get rid of that and then use analysis of flat cohomology in case of perfect algebras is, again, there's only H0 and H1, and one can express them in terms of Dieudonné theory, in this case due to Gaber and Akelau. Okay, so one first proves the desired identity in positive characteristic, and then one uses the star in positive characteristic to prove new properties of flat cohomology. New properties such as excision, for example, that was already used actually in the very beginning of the argument. So excision, descent with respect to the FPQC topology, FPPF, I mean, a priori FPPF cohomology need not satisfy FPQC descent, but it does with finite group scheme coefficients. That's several continuity properties, so on, and all these properties for flat cohomology, which really are statements that are not really, I mean, internal to what we're trying to do here. With purity, these are just properties of this cohomology theory that has so far been rather difficult to access. They are proved by reducing to the case of perfect A, perfect FP algebras A, and this reduction uses, again, derived techniques in the form of animated rings, upgrading these identities upgrading FPPF cohomology to animated rings and using the resulting added flexibility in intermediate reductions. It uses P-complete arc descent to handle somehow corresponding statements once P gets inverted, uses a bunch of other tricks. Anyway, okay, so one establishes these properties, and one actually, okay, so one uses them, one uses the new properties of this FPPF cohomology to prove star, well, to prove hyperdescent, P-complete arc hyperdescent. For the right-hand side, sorry, for the left-hand side in general. Okay, roughly this is how the argument goes, and okay, this is where I also finished. But let me just mention that in fact there are many other settings in which purity results are expected. For example, for torsors, for reductive groups, for algebraic K-theory. I already hinted at that, and well, it remains to be seen whether perfectoid methods could bring something new there as well. But it certainly was a priori surprising that they were very much relevant in these cases about cohomological problems that I discussed here. Anyway, there's certainly much that remains to be done on purity questions, and also on investigating, for instance, properties of flat cohomology. But for today, let me stop here.
Okay, great, thank you. Questions for Kęstutis?
Can you say a word about why it helps to use these derived methods?
Yeah, sure. So the way for example, the basic way how these, so all these properties, excision or descent, I mean, they're really about any ring. It doesn't have to be complete or something. But eventually, one wants to reduce to the case when the rings involved are perfect at P algebra. So one in particular needs to pass to positive characteristic in some way. And this is done by using continuity formula which says that if one has a B which is p-adically complete, say P complete ring, and one considers a PPF cohomology, say with coefficients in P power, well, find locally free group, one argues that this is actually the inverse limit of cohomologies of reductions of B modulo powers of P, but reductions in a derived sense rather than naive sense. So already here, already in the statement of this continuity, somehow derived these animated rings appear, because if B is not P torsion free, and sometimes it's just not so clear, not so convenient how to reduce to P torsion free case, this will have a non-trivial pi1 homotopy group, first homotopy group, and so I mean one already kind of lands inside this setting of simplicial rings or animated rings. It's anyways, these intermediate reductions really benefit from adding this generality, although the statements themselves are about classical rings, if you will, if you don't wish to enlarge them.
Thank you. Wait, sorry, a quick follow-up on that. If I assume that B is classically p-adically complete, is the version of this continuity formula true if I just did the naive mod P to the n? I don't assume bounded P torsion.
Well, you mean where I drop mod P to the n? I mean where I drop derived here.
Right.
I mean, a posteriori, yes, you could get such a formula in at least in higher degrees, because there's also a result that I mean, in H1 and higher, these are the same as I mean, the derived structure does not influence the higher H1s. So you could, if you want a statement on individual cohomology groups, you could somehow deduce it from this, and then hide the derived quotients a posteriori. But it's not that you know, you could prove. I don't think that actually proving it directly is much easier. It really helps.
I was really hoping you'd say there's an example where it's not true, and then I would just forget about this question.
Well, the point is that I think you could actually make a statement which is true for H2, H1. I mean, using this kind of identification gives a short exact sequence, of course, for cohomology of this in terms of limbs, and those statements will not involve the derived. Those statements will be less kind of functorial, but or less, you know, they will just be short exact sequences, but they will avoid the derived reductions.
But you say that in particular it's true, right? I mean, you have a map to the R limit for just the naive reductions.
Yeah.
And I guess a posteriori it follows that at least if B is classically p-adically complete, it's an isomorphism.
Yeah, okay. I agree. I mean, in cohomological degrees H1 and higher, it would.
Yeah, but on H0, I think it's also true just by inspection.
Yeah, right, because.
But maybe there's a limb 1 of the H0s that could be come wrong.
Well, a limb 1 of H0s will contribute to H1, right?
Right, but could this be a problem?
No, why?
Because the H0s are a priori different for the two things, and then the limb 1 Or are they different? I forget how everything works, sorry.
Perhaps.
Wait, sorry, can I ask another question?
Sure, go ahead.
So it's about this equality star.
Yeah.
This key formula. So the question is there some version of this when A is just a quasi-symptomic ring using the prismatic Dieudonné module?
Yeah, that's a great question. That also Akil posed some time ago. I don't know. I mean, presumably, or it remains to be found, but I don't.
I guess for G equals mu P there is. So I mean, surely the answer must be yes. But
yeah, I also strongly suspect that there is such a formula, and perhaps a posteriori one could hope that one maybe uses some of these methods to first establish such a formula rather than going in a very indirect route to prove it for perfectoids directly. But okay, that it has not been done, but this would be very nice.
Thanks.
It's probably hard to do it directly, right? Because you still need to know. You actually need to compute the FPPF cohomology, and this seems hard to get your hands at. Right?
Yeah, but at least you would have like various descent properties for FPPF cohomology, so that that would. Which are established in our paper, so that would could considerably help. Although they themselves are proved somewhat indirectly. So.
Yeah, I mean, I was hoping that like there could be some.
Everybody will think our paper is a big vicious circle after this talk.
Yeah, sorry, I was hoping that there was some comparison where you can just like, there's two objects you can write down, and then there's a map which is an isomorphism on H0 and H1 by the Dieudonné theory, and then maybe there's sufficiently locally, that's the only thing you have to check. But,
yeah, that would be great, but I don't know how to do that.
Sorry, yeah, other questions. I shouldn't monopolize.
I mean, even constructing a map is maybe not so evident. Like this, in the perfectoid case, a priori, we don't really exhibit any explicit map. We just work P-complete arc locally and then make sure that our identifications there are really functorial and canonical, but we're not, it's not like we first present like, aha, here's a map, and now we're going to prove. Well, it's not a contradiction that there could be, but I don't see it.
At least if you remove the supports and Dieudonné, so you should tell you that the H0 and the H1 agree, right?
Right, yeah, that's used essentially in a proof, yeah. Yeah, but I mean, even then, that's not quite the same as saying that there's a map which induces an isomorphism H1 and H0 and H1.
Right.
Sorry, is there no easy way to get a map by like using this description of the Dieudonné module in terms of like its classifying stack?
The problem is that this FPPF cohomology with supports involves the cohomology of the generic fiber, and a priori similar.
Sorry, yeah, in the non-support
only
case
works for
first.
P-complete rings.
In the non-support case, to get
okay,
a map.
In the non-support, yeah, in non-support case, you can probably get a map. I would guess.
Well, okay, let me actually mention that in positive characteristic, yes, A is then perfect, the supports disappear, and somehow we do get a map because we consider, I mean, this, we can use the fact that any class in H1 trivializes over some flat cover obviously, but then the perfection of that flat cover is still a flat cover of our perfect ring, which trivializes the class. And just by having the ordinary theory on perfect rings allows us to get some formula for M of G, I mean, psi theoretically, and then we get on cohomology. That's roughly how the proof of this formula works in positive characteristic. So there, I think it's a lot closer to what Bargan is asking. Basically, there the sheaf G is itself described as the Fischer-Boog invariance on M of G. As a sheaf.
Okay. If there are no more questions, let's thank Kęstutis again, and then we can continue this discussion for those who are interested.